The goal here is to just work another example of practicing our first time of doing confidence intervals here for one categorical variable. So again, first just reading through the example, let's pull out some important numbers. So we're looking at an assembly line that is interested in estimating the proportion of items that are defective. So a systematic sample of 1,500 items was taken, and we found that 45 of them were defective. So pulling out our important numbers here first, what we should be able to see is that our sample size is going to be this 1,500, and that our sample proportion, or p hat, will be the 45 out of that 1,500, or in decimal form here is 0.03. Hopefully it makes sense that we would actually want these numbers to be pretty small. We would not want to have a ton of defective items when we're on an assembly line. So the fact that our numbers here are going to be quite small is actually a good thing. Alright, so first we're going to go back and do some old terminology. So first let's talk about defining the population, because for once here it's not people that we're talking about. So here we'd be looking at all items on this assembly line. And then so what are we recording on those items? We're going to record if it's defective or not. So is that a quantitative or a categorical variable? Well, either is or is not defective, so it'll be a categorical variable. Right now we'll go through and do the new things. We're going to estimate the proportion of defective items with 99% confidence, and we will actually go to StatCrunch and verify those numbers as well. So I'm going to first do our conditions. So talking about first if we have a relatively random and unbiased sample here. So it says we took a systematic sample, so let's remind ourselves of what that is. So that would be like sampling every 50th item off of the assembly line. So every 50th I would grab one each time that way. And we did that till we had 1,500 of them. So that seems like a pretty reasonable method to me. Nothing I know about it is biased in any way. Then I need my n times my p hat to be at least 10. So if you'll notice, if I take my 1,500 times my p hat, which was the 45 out of 1,500, what we get back is just our number of defective items, which is at least 10. And then my n times my 1 minus p hat will be the 1,500 times 1 minus our p hat, or we're going to get back 1,455, because here was our number of defective items. Here's then the number of non-defective items, and it is also at least 10. Next, we're going to do our formula. So it can be nice just to pull up our formula sheet here real quick. So here's the formula that we see. We already know p hat is 0.03. We already know n is 1,500. So we just need to find our z. And so that was one of the ones that we talked about. So we do know that our z is going to be 2.576. Remember, those are numbers you can have written on your table. So now we have everything to plug in. So we have our 0.03 minus our z times the square root of our p hat times 1 minus p hat all over n. And then the same thing on the other side, except for we have a plus sign. So now it's just a matter of doing our order of operations correctly. So first going to do that square root piece. And again, I carry many decimals here, so I don't worry about rounding until the end. Same thing here on the other side. Next, we're going to do the multiplication. So taking our 2.576 times our 0.0044 number here, we get 0.0113, now rounding that to 4 decimals. And then again, it's the same number on the other side with just a plus sign between it. Then doing our subtraction and addition. So I get 0.0187, 2.0413, or percentage-wise, this would be 1.87% to 4.13%. And again, just trying to understand some terminology. So this square root piece, so when we did this number and got this 0.0044045, this is what we call that standard error. Once we multiply that by our z, that's called our margin of error. Or sometimes we just label as ME. All right, the last thing we just need to do is interpret it. So I'm going to write that in a slightly different color over here so you can see it. So I am going to be 99% confident that between 1.87% and 4.13% of all items on this assembly line are defective. Right, next part of the question asks us for the above interval, what was the standard error and what was the margin of error? Now those were two things I just explained, so I already have them labeled. If you were taking a quiz or a test and you were asked those, you'd want to go back and look at the math that you did here. So again, that square root piece, when I do that, so this 0.0044 number is going to be our standard error. Once we multiply that by our z, we get this 0.0113, which is going to be our margin of error. So our standard error, again, was that square root piece, so the 0.0044045 number. And our margin of error was once we multiplied that by our z, which was our 0.0113. Now, based upon our interval, could we conclude that the proportion of defective items was less than 4%? Why or why not? So looking at my confidence interval, it went from 1.87% to 4.13%. Is my entire interval less than 4%? Nope. So I cannot say that. So my answer here will be no, as part of the interval is higher than 4%. So again, even though that most of the interval is less than 4%, if part of the interval is higher, I can't say yes. So I'm going to have to say no here. All right, last here we're going to figure out how many items that they would need to sample in order to be within 0.5% with 95% confidence. How many items would they need to sample? So looking at my formula sheet here, this is going to be my sample size formula. So my Z is going to be based upon my 95% confidence. The margin of error is at 0.5% that they're telling me in the problem. And then P hat, I have to decide what we're going to use for that. So looking at my formula here, let's label some things. So for my Z, this time we're 95% confident. So my Z is going to be 1.960 from the numbers that you talked about in the video. My margin of error is going to be that 0.5%, but in decimal form, so 0.005. And for P hat, we just have to determine if we're going to use a 0.5 or the one that we had for our example. So they're still trying to do the same thing. So I can use my P hat from earlier. So we used a P hat of 0.03. So now I'm just going to plug everything into our formula. So we got our Z over our margin of error, all squared, times our P hat, times 1 minus our P hat. Then doing the math here, we should get 4,471.6. I can't only sample part of an item. Since this is a greater than sign, no matter what that decimal is, I'm going to have to round up. So if I have to sample part of the item, I'm going to have to sample the whole thing. So we're going to have to sample 4,472 items. All right, so hopefully that extra example scene worked out helps.